Hello, and thank you for joining us for the latest installment of the Pain Institute podcast. I'm joined with Professor Neal Sullivan, who is an associate professor at Colorado School of Mines in the Mechanical Engineering Department. Thanks for joining us, Neal.
Thank you, Jordy.
So you're doing some great work on fuel cells, and I was hoping you would be able to talk to us a little bit more about your research. I'm not particularly an expert on fuel cells, and I think a lot of our listeners aren't either. So I was hoping you might be able to explain it on a more basic level, and then we could possibly go into a higher level and then maybe some expert level. So if possible, it'd be great if you could explain it like you would to maybe like a 5-year-old.
Yeah, you bet. That's about my own level of understanding, frankly. So going after something I think we can all identify with, especially these days where we're spending so much time on the computer instead of face-to-face. We all are frustrated that our dang computers run out of power all the time. It drives me nuts. Why can't they just keep going and going and going? Why? Well, if I plug them into the wall, they can keep going and going. But, if I got my laptop, I want to sit outside, enjoy the sun, the birds, all that, right? But you can only do that for so long before that battery's going to die. And, to some extent, fuel cells can solve that problem. So everybody's batteries die. And fuel cells are a lot like batteries in the way they fundamentally operate. Essentially, we take a fuel, something with chemical energy. We use natural gas a lot, both the rest of the world and the lab in which I work, the Colorado Fuel Cell Center. We utilize natural gas a lot to fuel our fuel cells. But we take the chemical energy of that fuel and we turn it directly into electricity in sort of a one-stop shopping process, one step. And so that process of turning chemical energy into electricity is pretty nifty, and, that's what a battery does. Fundamentally, it's called electrochemistry. You use some chemistry to make electrons all at once. Electrochemistry. Big word, fancy. But the fact is, you're probably wearing 3 or 4 electrochemical devices on your body at this moment. A watch has a battery in it. A laptop, a cell phone. Everybody has these things, right? So electrochemistry is totally routine everywhere. And so one of the key differences between fuel cells and batteries, and everybody gets batteries. When you talk about a battery, my battery's dead, everybody understands what happened. Someone says a fuel cell's dead, they're like, I didn't even know what it was doing in the first place. One of the key differences between a fuel cell and a battery is that the fuel cell has an external gas tank. And so if I want to keep running my fuel cell, just fill up the gas tank and it keeps running. Now that's in contrast to a battery. When the battery runs out of power, we got to shut it down, plug it into the wall, and run it backwards. And when we run it backwards, what we do is we remake the fuel that we chewed up when we made up the electricity. So in the battery, just like your cell phone, the battery's got the fuel inside it. Not very much, but it's in there. All the fuel is in there and in that battery. So you don't see any plumbing on your cell phone or your laptop, or there's no plumbing for the fuel that go in and come out again, used up products. They don't have that. It's all inside. But the same process happens in that when you use up all the fuel, there goes all your electricity. It's done. So if we go plug it into the wall, then we run it backwards and we use electricity to make the fuel. And that fuel is captured in the battery itself. And then we can go use it again, go out and listen to the birds, that kind of thing. The fuel cell, we have an external gas tank. So we never have to shut the fuel cell off to keep making the electricity. We just fill up the tank, right? So some folks have heard about fuel cells for cars, and that would be one of the ways to do it. You got to fill the tank with probably hydrogen, but nonetheless, the same kind of thing holds. And so, I tell people about fuel cells, they have this blank look on their face. What does it even do? Well, the fuel cells make electricity. They turn fuel into electricity, electrochemistry, just like batteries turn fuel into electricity. So when I say batteries, everybody knows what I'm talking about. When I say fuel cells, nobody knows what I'm talking about. So I've found myself saying batteries a whole heck of a lot more, just so people understand or think they understand what I'm talking about. Now, the fact is, when you get right down to it, how does a battery actually work? How does that chemical energy get turned into electricity? Well, there's very few people that can answer that, despite all of us understanding what batteries are and what they do. We all value what they do. When it comes right down to what they do, electrochemistry, most of us don't know what's going on in there. And rightly so. I can't say I got a problem with that. I don't blame them. It's just more about making people comfortable with the technology that you're working on and bringing people to where you are in the research effort. Now, a lot of the problems we have with batteries, the things that frustrate all of us with our batteries, are the same problems that we work on in the Fuel Cell Center for our fuel cells. The same things. I'll give you an example. My laptop. When I first bought my laptop, I could fly from the United States to Europe on a single charge. I didn't need to plug the thing in. I was good to go. The battery lasted a long time. Well, now it doesn't do that anymore. Now I get halfway across the Atlantic and I'm done. So why is that? Why is my battery dying? Well, it's the same reason the engine in my car doesn't quite work as well as it did after the first few hundred miles out on the road. Same reason anything wears out. It just degrades. Performance degradation. Things happen. You use it long enough and all kinds of little internal resistances start to grow. I mean, you just can't use a battery forever. Well, you can't use a fuel cell forever either. So a big effort for us is how and what and why do our fuel cells die over time? Why is there big performance degradation? And so we put a lot of effort into that, and that gets into some pretty specific focused stuff. Looking at one little interface between one thing and another thing and the chemistry and all that. I mean, it's hardcore. But those are the kind of things that you got to address if you want all the people in the world using fuel cells like all the people in the world use batteries. So fuel cells make electricity, and that's cool. And there's a lot of ways to make electricity. And that's actually a problem if you're in the fuel cell business, because who really needs your device? There's a lot of ways to make electricity. Why would I want a fuel cell to do it for me? And that's a pretty legitimate question, especially if you're trying to make a business out of it. Because actually, most of us don't really care what's behind our electric generator. We just want the electrons. We just want electricity. I don't care if it's a fuel cell or a gas turbine engine or a battery or the sun or the wind or whatever. I mean, I kind of care. I'm into everybody likes saving the world here. But really, I just want the electricity. So why do I want a fuel cell? And there is an answer to that question. And the answer is the fuel cells are considered to be, and are pretty much accepted to be, the most efficient way to turn chemical energy into electricity. You're going to get more electrons per gallon of gas with a fuel cell than with just about anything. You know, there's very few things that are going to compete at that efficiency. So the fraction of chemical energy that gets turned into electricity is super high with fuel cells, pushing 70%, whereas most generators it's down around 35%. So that would mean I'm going to need twice as much fuel to get the same electricity, which who likes that, right? Nobody likes that. And that's true. So with fuel cells, you could save a lot of money on fuel. And who doesn't like that? Everybody likes that. And you're decreasing the amount of pollution you make, and we like that too. But perhaps you're aware, perhaps you've noticed, the price of fuel is incredibly low. And so if I waste some, hey, you know what? It's no big deal. I've got plenty more. It's dirt cheap. And then in contrast to that, so that kind of cuts into the motivation to get a fuel cell to do the job anyway, because you just waste a little fuel with your existing generator or your lower quality one or your more polluting one, but whatever. So I waste a little fuel, whatever. So that kind of cuts into our marketing for fuel cells. So fuel is super cheap, and we're not greatly motivated to save it. So that kind of cuts into the marketability of fuel cells. Another thing about fuel cells is that they're pretty expensive. You know, to buy them up front, you got to pay more than the existing generators that are well established, existing electric generators that are out there. You got to pay more, and no one likes paying more. But you know, you can argue, hey, you're going to make your money back by saving all the fuel. Well, that's true if fuel's expensive, but it isn't. So that market's kind of getting tough. And then lastly, fuel cells generate far less pollution than conventional generators like engines and whatnot. But you know, no one likes pollution, but it's not like it's regulated. It's not like you're going to get punished for spitting out too much pollution. So we're not really motivated to use these fuel cells to make electricity. The motivation is not overwhelming in this country. Other places, there are motivations, but in this country, it's a little tough. So one of the things that I'm really excited about with fuel cells is not so much making the electricity, which we talked about. It's storing the electricity. So we talked about with batteries, you're going to plug the battery into the wall outlet to charge her back up again, make fuel. You're going to take electricity out of the wall, make fuel. And that's what we're trying to do in the Fuel Cell Center with excess solar and wind power. We're going to use it to make fuel using our fuel cells. But actually, we run the fuel cells backwards, just like we run the batteries backwards when we're charging them up. And again, once again, the key difference being that the fuel cell in reverse has an external gas tank. So I just keep filling up that gas tank with the solar and the wind power that I was harnessing. And then I switch out a new gas tank. And then I can just keep doing this for as long as I want. And meanwhile, the solar and the wind, that just keeps coming more and more online. Market penetration, we're getting more and more gigawatts of that stuff. And who doesn't like that? I mean, is anybody against solar and wind? I don't think anyone in the country, the world is against solar and wind. We all want more of that. But there's some problems with that, like nighttime. That's a problem. No more solar. And then sometimes the wind stops blowing on a nice day, and then no wind power. So that's a problem. Those are big problems. We want continuous power. And so what we need to do is come up with a way to store that solar and wind. And in contrast to making electricity with fuel cells, in contrast to that, well, there's a lot of ways to make electricity. There actually aren't that many ways to store electricity. There's a lot of ways, but they're not very good. The fact is the batteries have a limited storage capacity. You can only stuff so many electrons in there. You can only make so much fuel in that battery because it's a closed volume, Whereas the fuel cell has this external tank, well, we can just keep dumping it in there. And if the tank fills up, all right, I'll switch the tank out. But that's not that hard. So the fuel cells in reverse, we call those electrolyzers, electrolysis. And we can essentially make chemicals that are of great value to us. Those chemicals are fuels, right? We run our fuel cells backwards as electrolyzers. We take the solar and the wind power, drive our fuel cells in reverse, electrolysis, we make electrolyzers. And we use those electrolyzers, those fuel cells in reverse, we use those electrolyzers to make fuel. Maybe hydrogen, maybe methane, maybe ammonia. We get a long list of things. So we have a lot of different projects about harnessing solar and wind power to make chemicals that the world needs. So we're trying to store solar and wind in the form of chemicals. These are electrolyzer projects, energy storage. So energy storage is a huge topic, and one in which I think the Colorado Fuel Cell Center can make some pretty important contributions. And finally, it's one that everybody understands. Nobody understands fuel cells. Nobody understands electrolyzers. Everybody understands nighttime. Everybody understands the wind stops blowing sometimes. Everybody understands the need to store the solar and the wind power so that these fluctuations can be smoothed out. And so that's where I have a lot of excitement for the future of our laboratory and the future of the School of Mind's role in answering some of these questions.
Well, thank you. That was great. I can tell you're very practiced with that kind of explanation. And I guess that comes, from our lack of understanding of fuel cells and batteries. And I really appreciate some of the points you made, especially, solving the problems for solar and wind, because that's something that a lot of people are worried about with the future of renewable energy. The wind stops blowing, the sun stops shining. And I feel like I'm much more knowledgeable about fuel cells now. Even the fraction of chemical energy and the most efficient way to convert chemical energy into electrical energy, like that all makes a lot of sense to me now. The next step would be to go a little bit more in depth if you could. I mean, that was a great explanation. I feel like even for a college student would appreciate that. And I learned a lot. But I know you're doing something more specific with them now. So you're not necessarily just doing general fuel cells, and you guys are at the forefront of this type of research. So maybe you could talk a little bit about that. I think maybe I'm still a little bit confused on ceramics, some of the benefits of ammonia, because everyone always talks about hydrogen fuel cells, but I feel like, you mentioned ammonia and ceramics to me were always kind of what you made plates out of, and I'm not really sure how they fit into
right
how they fit into the fuel cells. But I mean, I was too afraid to ask if I ever talked to a fuel cell expert.
No, it's a highly legit question, and I'm glad you asked it because it's something I often blow off. And I have to say, it does increase the level of discussion because now we're going to start talking about the specific materials from which our fuel cells and electrolyzers are made. And there's a lot of different materials. And, to try and draw parallels to other technologies, I'll go back to the battery. Many people could spit out 3 or 4 different kinds of batteries without any idea of the meaning behind the words they're saying. And that doesn't make them bad people. It just shows it just shows the ubiquitousness of batteries in our world, right? Like NiCad. How many people have heard of a NiCad battery? A lot. How many people have heard of lead acid? It's the one in our cars. Fewer, but that used to be the only one back in the day. That was pretty big. Now it's all lithium ion. What does that mean? Lithium air. So all these different names are just all these different material sets that have proven to be pretty good for doing this electrochemistry thing we were talking about. There's a long story behind those materials, but just as there are many different materials that make up batteries, lithium ion, lead acid, NiCad, whatever, just as there's a lot of different materials that make up batteries, there's a lot of different materials that make up fuel cells. And the ones that we put a lot of effort in at the Colorado Fuel Cell Center, the ones we put a lot of effort in are ceramics based. We call them solid oxide fuel cells. I think that's all part of the poor branding we have for fuel cells. Solid oxide, what does that mean, right? Well, it's ceramic, just like you said, like coffee cups and plates. So why don't we call them ceramic? I don't know. Why do we call them fuel cells? When you hear the word fuel cell, do you think electric generator? No, you don't. Nor do I. In fact, I can still remember when I first heard it while interviewing for a job at a fuel cell company. I thought it was like this hydrogen, like this amoeba, this living thing, that the cell that was going to make the hydrogen, just belching hydrogen periodically, the fuel cell. That's what I thought they were. No, they're ceramic, like coffee cup material. Okay, so that's a long way. That interview didn't go that well. Should have done my homework a little more. The ceramic part, so we like the ceramic ones. And those are the ones we pursue a lot, but actually that's not the most popular one. The one that's the most widely used in the world today, whether you're talking about fuel cells for making electricity or electrolyzers for storing electricity, the most popular one is called a polymer electrolyte membrane fuel cell, PEM fuel cell. And we do studies on that here at Mines. They're primarily led by Professor Andy Herring in the Department of Chemical and Biological Engineering. And they get a good thing going there. I mean, that's actually very robust, healthy research underway. And I'm not here to diss it. I mean, that's a big effort. That's what the fuel cell cars were going to be built on. But they kind of have some limitations, like take the polymer part, like the polymer plastic. It's plastic fuel cell. And so plastics can't get very hot, and they're just going to melt. And so those fuel cells, they just don't run very hot. They run at like, I don't know, 100 C, probably a little less. So 200 Fahrenheit, which might sound kind of hot, but actually it's pretty tough to get chemistry to happen, whether it's electrochemistry or whatever. It's pretty tough to get that to happen down at those kind of lower temperatures. And so to get it to happen, you got to use some materials that you'd rather not use. You might have heard of platinum being a big issue in polymer electrolyte membrane fuel cells, because you got to put platinum in there to get the chemistry to happen, because chemistry doesn't happen at 100 C. So we got to put that stuff in there. That gets a little pricey. And then we got to use a really clean fuel. We got to use hydrogen fuel for the most part. That's not entirely true, but for the most part, hydrogen fuel is the only one that really works very well because it's so simple. We can get that chemistry to work pretty well at those low temperatures. So we've had to make a lot of changes to get that fuel cell to work right. And the fact is we don't have a lot of hydrogen around. It's kind of a hassle. Hydrogen's a hassle to deal with. It's tough to store. It leaks through everything. Super light, the energy density is terrible. You need a giant gas tank. It has its shortcomings. It has its strengths too. Like you can drink the exhaust. The exhaust is water. So, okay, that's pretty cool. But I'm not actually short on water. So after the novelty wears off, that's not so great. Now, us ceramics guys, well, our ceramic stuff doesn't work at low temperature. It just isn't going to happen. You try to get it to run at 100 C, forget it. It's just going to get nothing. So we got to get hot. You got to get up to like 500, 600, 700, maybe 800 C, right? 800 C. So what's that? That's 1500 Fahrenheit. That's 3 times as hot as the furnace as the oven in my house can go. That's hot, okay? So that brings new challenges, but it also brings some nifty new solutions. Like the chemistry ain't so hard anymore. Things are pretty hot. So you don't need the platinum anymore. And that brings the cost down substantially. So that's good. And then you can use dirty fuels. We can use natural gas. That's the big thing. Well, we got enough natural gas for 100 years. So better start thinking about how to use that the right way. And our ceramic fuel cells can do that. And other types of fuel cells have more challenges with that. I mean, they can do it, but it's a lot more work. And our solid oxide fuel cells can do that quite well. In fact, it's great for the efficiency. You can store a lot more energy in that natural gas than you can in hydrogen. And that makes a big attraction for us. So that's one of the reasons we're behind the ceramics. And another one is actually, this is kind of fun, it's the history of mines. You know, fact is, mines has a long history in ceramics research, and that's evidenced by the Colorado Center for Advanced Ceramics and all the efforts from the ceramics team and in Hill Hall in the Department of Metallurgical and Materials Engineering, many of whom are my collaborators and good buddies. And it's evidenced by the existence of Coors Tech. Coors Tech here in Golden is the largest ceramics company in the world. And so the Coors Tech family has had a huge impact, a huge positive impact on mines. And some of that goes with the direction of the research pursuits that we are taking. And in fact, one of the most advanced fuel cell materials we're working on right now is called a proton conducting ceramic. And really all of this work, we have a big team on that. We have the biggest team in the United States, one of the two biggest teams in the world in this field of proton conducting ceramics. It's getting a lot of attention now. And all of that was inspired by Dr. Grover Coors, who earned his PhD at Mines, member of the Coors family, member of the Metallurgical and Materials Engineering Department as an adjunct faculty member. I mean, long history there. And that history plays a role in the directions that Mines takes in its research. And I just think that's kind of fun. I mean, that's a cool extension and reasoning behind Mines doing what it's doing. In addition to making impacts on the nation and in our energy infrastructure, we're also kind of drawing on our history and our skill sets from decades and decades of partnership with local companies. And so I think that's kind of fun. Yeah, so that's a little bit on the ceramics. And like you said, you know, ceramics for coffee cups and plates. And that is a big selling point for our so-called solid oxide fuel cells, our ceramic electrolyzers, is because they are coffee cup material. They are moderately priced. We can make a lot of them at a reasonable cost. There is no platinum in there. They're kind of cheap materials. And when you're trying to make a cheap electric generator, because all the other electric generators out there are cheap, using cheap materials is a good way to go. So that is a big motivating factor for us in the Colorado Fuel Cell Center.
Thank you for that. Yeah, I loved some of those insights. You know, it's cool to see how multifaceted some of these approaches are. You know, you talked again about renewables, but also natural gas and just like the multiple applications that we could use with this. And I think that's something that's kind of missing from a lot of these conversations is how we're going to solve some of these more technical and limitation problems. And it seems like you guys are on that. I mean, you know, you talked about, you know, different chemistries, different approaches, and it seems like it's a very exciting field to be in. I actually met Grover Coors once. I remember being surprised to hear about the Coors family, you know, playing such a large role in fuel cells. And I think most people will be as well, you know.
Yeah.
At Mines, I'll go ahead.
Well, what I was going to say was you kind of brought up the different perspectives. And I have to say, when it comes to working at Mines and being part of this Colorado Fuel Cell Center, the range of perspectives on this topic, broad topic, not fuel cells, not electrolyzers, but energy. The range of perspectives for me is the coolest part of it all, you know. And the Payne Institute has a role in that. The policy, the techno-economics analysis, the life cycle analysis, the systems engineering. So, you know, I've been talking about ceramics and fuel cells and batteries, and we do a ton of that, right? We got a material science program. We've got a metallurgical materials engineering department. We got the mechanical engineering department. These are materials people getting nitty gritty. You know, what's the ionic conductivity of the barium cerate at 600 degrees C in a 20% steam environment, the hydrogen, you know, blah, blah, blah. Only techno-weenie stuff that material science people are going to get into. But it doesn't end there, you know. We also got the guys over in mechanical engineering. You get Professor Rob Braun doing systems analysis. You know, if the fuel cell runs this well and I got to make a gigawatt generator, how big is the generator going to be? What's the materials cost? What's the bottom line efficiency? What's the life cycle analysis? I can't do any of that. I don't do any of that. But the data we get in the lab goes right to his models to do that kind of thing, him and his students. And then there's the controls guys. You look over in electrical engineering, you get Professor Tyrone Vincent talking about, well, how are we going to operate the device for part load conditions? How do we turn it down while it still maintains efficiency? You know, what are we going to worry about frying when we're only operating at 25% power? You know, totally cool perspective there. And then you get, like I was saying, the Payne Institute. You guys, how can the policies of the federals or the state levels, how can those policies assist the growth of this market or impede the growth of this market going forward? Where are new markets going to be emerging? Where are the hot spots where we can make an impact? And the range of study, I think, is so cool just because it's so different from all these different perspectives, but also the opportunity for the student. Students from every department, from every field can play a role here if they can find the right match. And I just think that's what the School of Mines is supposed to be about. And I see it happening all the time. And it just makes it a really fun place for me to work.
Yeah, no, I agree completely. And I appreciate the introduction to the term techno weenie. I think that's a great way to describe mines. Personally, yeah, I mean, it's kind of seems like we're in a, data at mines feeds into other data and other projects. That's something that's great about mines. At the Pain Institute, we work a lot with, the mining industry and their development. So it's nice to be able to go talk to the mining department and then find out they're talking to, another department about renewable integration and, like you're saying, like systems processing to see how they're solving that problem. And then it's very cool to see, that at mines we have multiple steps of the process and that we're all kind of, it feeds into each other. It's a very cool subject. And
I think it's really what's been able to make mines and the Fuel Cell Center and the Colorado Center for Advanced Ceramics. I really feel that what's made us one of the nation's leaders. The range of capability that isn't just talk. I mean, it's actually being done with research published and high, clear evidence of the efforts, and not just chit chat and a nice web page. So I'm excited about that.
Yeah, me too. It's great. Yeah, I went to mines and I didn't get to do cool research, but I'm doing cool research now, so I feel like that's making up for it. Speaking of research, you guys have been doing some great research in your lab, and something that's a little bit more on the forefront of fuel cell technology. If you want to speak a little bit about that, maybe for some of our more technical listeners that might appreciate some of the advances you guys have been making.
Okay, yeah, I'll give a shot at that. It's tougher to do over audio, but nonetheless, we can do that. So one of the things we're spending a lot of time on is tuning our materials for the different applications that they may see. All right, let's see. Let's consider. Well, we talked about these proton conducting ceramics, so that's a hot topic for us. And so these proton conducting ceramics have a lot of different elements within them. All right, like we talked about the toilet bowl, the coffee cup, the plates. I mean, those are essentially all the same material or very similar material, and that material is aluminum oxide. It's aluminum with a couple of oxygens stuck on the outside. Super stable, hard as a stone. I mean, you can beat the crap out of it; it ain't gonna do nothing. And that's a nifty material that's very low cost, and it makes good plates and good toilet bowls, right? But it's super simple, and it's not going to do any electrochemistry for us because it's a bit too simple. So what we've been doing is putting together some pretty unusual materials to form these ceramics that enable them to have these properties that are good for electrochemistry, for turning chemical energy to electricity. Like the one that, let's submit this paper today on a material that includes barium, which is kind of scary, barium, cerium, zirconium, yttrium, ytterbium oxide. That's a mouthful, right? BACEZRYYBO3 or something. I mean, that is, what? What is that? Right, so we get 5-6 different constituents in the material. Well, what? How did you get there? The fact is, I don't even know how we got there. There's a long story behind that. There's decades of history behind the development of these materials. And they're so wacky that they never got anywhere. They've never gotten past, well, when we make the device out of this material, we make the fuel cell, the electrolyzer out of this material, we make them as big as the button on your shirt. In fact, we call them button cells because we can't make them any bigger. One, because we're a university, we just don't make big stuff. But two, because the materials are so wacky, really, no one can even really make them that big before. But now we got all these new projects, and the Department of Energy has been investing in us to get beyond the button cell, to make the device in a way that would enable folks to make megawatts, right? Now, we know Mines isn't going to make megawatts, so we go and partner with companies. One of those being Coors Tech, another one being Fuel Cell Energy, a company out of Connecticut, one of the best fuel cell developers in North America, oldest fuel cell developer in North America. And so they take the things we've learned with the material sets we've created, these barium, cerium, zirconium, all that, and they scale it up to, well, instead of the button on your shirt, the plate at the dinner table, literally, or the CD that, well, I guess no one's really using CDs anymore, but if you did, they look a lot like the fuel cells we're making, or I should say Fuel Cell Energy's making. And one of the things we've been doing a lot at the Fuel Cell Center is trying to understand how to do the mixture of the barium and the cerium and the ytterbium and the yttrium. Just how much of each do we put together to get the performance we want? Well, when you're putting in 5, 6 different components, you can imagine there's a lot of different mixtures you can make, right? And most of them ain't going to work, but that's our job, to figure out which one does, right? And then when you say if they work, well, that's kind of a general term. Work at doing what? I mean, we just talked about applications involving storing electricity, applications involving making electricity, applications making fuel. You can imagine that different materials will be better at one of those 3 things than others. And so tuning the material to meet that need, well, that's something we spend a lot of time on, materials development. That's kind of hardcore nitty-gritty material science. How does this material operate, function? What is its ionic conductivity at 600 C in a 50% hydrogen environment, 20% steam, stuff like that. So materials development is a big part of what we do in the Fuel Cell Center. I hope that talks to your question a little bit.
Yeah, no, that was very helpful. Thank you. And I think that's something that a lot of people are kind of missing about, what type of research is being done specifically for fuel cells. And for me, it kind of echoes a lot of what I see with lithium ion batteries, the chemistry of, nickel, manganese, cobalt in the different parts of the battery. And no, that was very helpful. And I think that you guys are doing great research, and I appreciate you taking the time to interview with us and to tell us more about it. And I hope that we can connect in the future as well.
You bet, Jordy. It's been a pleasure.